Okay, last time we studied many sets that had cardinality Aleph null, the same cardinality as the natural numbers. Natural question, are there larger sets? Turns out the answer is yes. We will prove that today. In particular, here's a definition. We say that a set A is uncountable if it has cardinality strictly larger than that of the natural numbers. In particular, what this means is that there's an injective map from the natural numbers into the set A, but there does not exist a bijection from the natural numbers to the set A. Okay, we're going to define what's called a decimal expansion. So here's some definitions. We say a digit is a number in the set 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. What we think of as a digit. A decimal expansion is an infinite sequence of digits. We write the value of such an expansion, sometimes we'll denote this as rho of the expansion, as given by this sum. We take each digit, divide it by an appropriate power of 10, and then add these up. We can also write this as 0 dot d1, d2, d3, d4, and so forth. This is what we classically mean when we talk about a decimal expansion. Okay, now we're going to state a theorem about decimal expansions. We're not going to prove this for now. This is something one would prove in a real analysis course, but it's a reasonable theorem. The theorem says two things. The first claim is that every decimal expansion evaluates to a real number somewhere inside the closed interval 0 to 1. Specifically, what I mean by that is whenever I choose any choice of digits and I compute this sum, I get a real number in 0, 1. The second part of the theorem tells me about the cases where a particular real number might have multiple decimal expansions. And here's the claim. The only time a real number can have two decimal expansions is in a situation like this, where one decimal expansion ends in an infinite number of zeros and the other ends in an infinite number of nines. Otherwise, there's a one-to-one correspondence between real numbers and decimal expansions. As I said, we won't prove this today. We'll take this as a given. Okay, so here's an example of where we might have a non-uniqueness here. If we think about the real number 0.125, we can add an infinite number of zeros after 0.125, or we can also look at the expansion 0.124999999. Those give us the same number, but the only way we can have non-uniqueness is some sort of pattern like that. So to be more explicit, any decimal expansion that does not end in an infinite number of zeros or an infinite number of nines corresponds to a real number with a unique decimal expansion. Okay, now we're in a position to prove that there's an uncountable set, and specifically, we're going to prove that the closed interval to 0 to 1 is uncountable. The type of argument we're going to use is commonly called Cantor's diagonal argument. This is, of course, named after the famous mathematician, Professor Diagonal. I joke, it's Professor Cantor, and the diagonal part comes from, as you see in the construction, where we're going to take a diagonal of a bunch of sequences. More on that in a moment. Here's how we go with the proof. Let's assume that we can list all of the elements of the closed interval 0 to 1. So specifically, R1, R2, R3, R4, Rn, keep going. It's an infinite list, but we're listing them. And these are all numbers in the closed interval 0 to 1. And specifically, the claim is that every element of that interval is in this list. Okay, every one of these real numbers has a decimal expansion, so let's just write out the decimal expansions and order it this way. The real number R1, we're going to call the digits D11, D12, D13, and so forth. The real number R2, we're going to call D21, D22, D23, and so forth. And we basically get this big array of numbers. Now what we do is let's concentrate on the diagonal elements, the DII. So basically we're looking at the ith digit of the ith number. Let's go through that list. Anytime that number is not 1, let's write down a 1. Anytime that number is 1, let's write down a 2. So we're defining the sequence EK so that it disagrees with the diagonal term everywhere. So notice that the EKs are all either 1 or 2, and specifically there's no zeros or nines here. And if we write down the sequence E1, E2, E3, E4, E5, this disagrees with everything in our list, because since E1 is not equal to D11, it disagrees with R1 in the first spot. Since E2 is not equal to D22, it disagrees with R2 in the second spot, and so forth and so on. So what have we done? The sequence that we just generated is a decimal expansion of a real number that does not appear in our list. In particular, what we've really shown is that for any list of numbers in 0, 1, we can construct a number that's not on our list. That implies that no list can contain all of these elements, and if no list can contain all these elements, the set is not countable. Okay, we have shown that the interval is not countable, which means that there's no bijection between the natural numbers and the interval. But what if, I don't know, the interval is like smaller than the natural numbers, something like that. So let's make the point that the interval is at least as big as the natural numbers by showing an injection. In particular, we're going to demonstrate an injection from the natural numbers to the interval. In fact, here's the formula. We send 1 to the decimal expansion 0.1000. We send 2 to 0.01000, 3 goes to 0.001000. In particular, we send n to 10 to the minus n. That's clearly an injection. It clearly maps the natural numbers into the closed interval 0 to 1. As such, that means that the cardinality of the natural numbers is less than or equal to the cardinality of the interval. Since we've also shown that the cardinality of the interval is not the same as the cardinality of the natural numbers, that means that the cardinality of the natural numbers is strictly less than the cardinality of the interval. One more note. Also notice that the interval is a subset of the real numbers. In particular, we can write down an injective function where we map the interval to the reals by just taking f of x equals x. So, the cardinality of the interval is less than or equal to the cardinality of the reals. And since it's strictly more than the cardinality of the naturals, that means that the cardinality of the reals is strictly more than the cardinality of the naturals. In particular, the real numbers are also uncountable. We will show in the next lecture that the real line and the interval have the same cardinality, although we haven't shown that yet. This cardinality is sometimes called the cardinality of the continuum. Okay, we've shown that the real numbers have cardinality larger than the natural numbers. And let's be honest, let's let that sink in for a while. That's kind of weird, right? We have two infinities and one of them is bigger than the other. Kind of wild. But then we might think, well, wait, maybe the cardinality of the real numbers is the largest possible number. But the answer is no. That is not what's true. In particular, we're going to prove a theorem that says the cardinality of any set is strictly less than the cardinality of its power set. The bottom line is there's always a bigger set out there. So R is not the largest because the power set of R is bigger. And that set's not the largest because the power set of that is again strictly bigger, and so on and so forth. Okay, let's prove the theorem. First of all, we're going to show that the cardinality of A is less than or equal to the cardinality of its power set. The way we're going to do that is by demonstrating an injection. And here's one. If we have the map from A to the power set of A that sends X to the set only containing X, we can check pretty easily that that's an injective function. That implies that the cardinality of A is less than or equal to the cardinality of the power set of A. Now we need to show that there is no bijection from A to its power set. What we're going to do is we're going to assume that we have a surjective function from A to the power set of A and obtain a contradiction. Assume that G from A to the power set of A is surjective. Note, let's think this through. G takes elements of A as inputs and returns subsets of A as outputs. For any x in A, g of x is a subset of A. So notice for any x in A, either x is in g of x or x is not in g of x. So let's let S be the set of all x in A such that x is not in g of x. That's a subset of A, therefore it's an element of the power set. By assumption, G is surjective, therefore there must exist a Z in A such that G of Z equals S. So again, to summarize what we have, is we define S to be the set of all X such that X is not in G of X, and we know that there exists a Z in A with G of Z equal to S. So here's the big question. Is Z in S or no? Well look, if Z is in S, remember S is G of Z, so Z is in G of Z, so Z is not in S. That's a contradiction. Okay, so what if Z is not in S? Well then Z is not in G of Z, but then by definition, that means it's in S. Another contradiction. Either way, assuming that Z is in S or Z is not in S goes to a contradiction, That means both of them are false, but they can't both be false. That's absurd. Therefore, our original contradiction is with the assumption that G was surjective. Okay, we're going to go over this argument one more time and look at the diagonal argument in kind of its full generality. Let's start off by assuming that A is a finite set. Let's call its cardinality M. It's a finite number. Let's also assume M is at least 2 to make things interesting. Let's define A to the n as the set of all vectors of length n where the components are in A. In this context, this is sometimes also called the set of strings of length n over the alphabet A. We'll use both terminologies here. We also want to consider the set of infinite strings over A. That is, vectors of the form A1, A2, A3, all the way to AN, and it keeps going where all the AIs are in A. We're going to define A star to be the set of all finite strings over A, and we're going to let A omega be the set of all infinite strings over A. And here's the theorem that we're going to prove. We're going to prove that A to the n is finite. We're going to prove that A star is infinite but countable. And we're going to prove that A omega is uncountable. Said colloquially, we might say bounded strings give a finite set, finite strings give a countable set, and infinite strings give an uncountable set. All right, now let's prove this. We first note that the cardinality of A to the n is actually the number m raised to the power n. To see this, we get m choices in each slot of the vector, and there's n slots. So we have m times m times m, n times, that's m to the n. Okay, now let's consider A star. We're going to write all of the finite strings in order. So we're going to write all the strings of length 0, there's one of those. All the strings of length 1, there's m of those. All the strings of length 2, there's m squared of those. At each stage, there's a finite number of strings, and we just keep concatenating them, on and on and on. I claim that every finite string appears in this list somewhere. Let's see. Let S be a string. It has a finite length, let's call it n. I claim it should appear in no later than this place where we take the sum I equals 0 to n of m to the I. To see that, remember we have all the strings of length 0, then 1, then 2. All the strings of length n are going to appear in this area that is numbered no higher than 1 plus m squared plus m cubed all the way up to m to the n. That's a large number, but it's finite. Therefore, S will appear at some finite index in this string, and we're done. Since we can list all the strings, the set is countable. Now, let's consider A omega. Remember, A omega is a set of all infinite strings. Let's assume that we have a list of these strings. Let's call it S1, S2, up to Sn, and so forth. We're basically going to use the same diagonal argument that we did earlier. So if we write out the entries of S1, call it A11, A12, A13, and so forth. S2 is A21, A22, A23, and so forth. We just write all these out. We kind of get this big array, and then we go down the diagonal. But what we do is everywhere we have this diagonal term, let's just pick BI to be anything not equal to AII. So B1 is anything but A11. B2 is anything but A22. B3 is anything but A33. The same diagonal argument is going to hold as before. If we look at the string B1, B2, B3, and so forth, it disagrees with every string in this list because it disagrees with the first string in the first place. It disagrees with the second string in the second place, the third string in the third place, and so on. Therefore, we have shown that there exists a string not in this list. And in fact, I'll just remark, we've actually shown there's a lot of strings in this list. Because remember, as we're going down to the diagonal, we can choose anything, BI, that's not equal to AII. So in fact, at every one of these places, we have n-1 choices. Ton of strings that are not in this list. But in any case, we've written an arbitrary list of these strings and shown that there are strings that are not in it. Therefore, A omega is uncountable.